last part of this lesson. What is system phase response, and why is linear phase response a big deal? First, what system phase response in general? We're talking here about what the angle is, what the phase is of the system. And it's so important that we give it its own moniker. We call it theta of omega, or the system phase response. What I want you to think about with this is that if you put in a cosine of some sort of arbitrary frequency into your system, you know you're going to get out that exact same cosine, just modified by a magnitude and by an angle. And if we call the magnitude capital A and we call the angle theta, then hopefully it's clear that what this magnitude is and what this theta is a function of what this frequency is. Now, this A is the system gain. It's the gain of the system. And this theta is the system phase. And you can calculate it. It's a complex number by just plugging in for Z, e to the j omega naught. And this will be a complex number. Its magnitude is this system gain, and its phase is this system phase. And that's what we're talking about with this phase, is it's just the phase of the system at a particular frequency. Your thought process into it is that if I put in a cosine of a particular frequency, how much I'll get out that exact same cosine, how much will that output cosine be shifted by that phase at that frequency? Now, there's a special case of this phase function. If it's equal to minus some kind of constant times omega, then we say it is linear phase. And by linear phase, what we really mean, it's a confusing term, isn't it? What we mean is that if we were to graph what our phase is, that phase function drops like this. And that slope is equal to minus times some integer. And that slope is equal to minus some, and that slope is equal to minus some constant. So why is it important? To understand why linear phase response is important, imagine a system that we want to design that doesn't change the shape of the input. It just simply delays it by 1 unit. Now think about what that means in terms of how much it delays the phase, what its phase function is. If you want to delay this by 1 unit, and I'm drawing it as continuous time, but I hope it's just too hard to draw it with lots of stamps. If we want to delay this thing by 1 unit, by this much, no matter what its frequency is, we want to delay it by this much. Here, for this low frequency, that's equivalent to a delay of 360 degrees. You can see it's one exact cycle. Now let's do this again, but for something that's twice as high frequency. So it goes up here. So this is twice as high frequency. And when it's twice as high frequency, now we want to delay it not by 360 degrees, but we want to delay it by 720 degrees. Let's do pi's because it's easier to count pi's. 2 pi delay, 4 pi delay. Let's say we want to have it a higher frequency yet. So now it's a 3 times higher frequency, and now we want to delay it by 6 pi. So in general, the amount that we want to delay it is proportional to its frequency. And that's exactly what linear phase response is it's something whose delay, it's something whose its phase amount that's added onto it is exactly proportional to the frequency. The higher the frequency, the more phase delay, and that means that you recover the exact same shape of the signal, it's just been delayed. So this is the intuitive answer, and this is how I think of it in my head, but that's because I'm not a mathematician. A mathematician would say that a system that delays things by 1 unit would be this, z to the negative 1. And that has an e to j omega of e to the minus j omega. And you can write that as a magnitude of 1 and at a phase of minus omega. And so there you have your system that has a linear phase response if it keeps the shape of the input unchanged, but it just delays it by some amount. Now, this particular example, I had it delaying it by 1, but in general, a delay of any amount would be this. Now it will delay our input signal by k units to the output signal. And of course, its dTFT would be e to the minus j k omega. And that's the same thing as having a magnitude of 1 and a phase of minus k omega. And so a system that delays things exactly by k units and doesn't change the shape is something that has a linear phase response. And the opposite of that's true too. If a system does not have a linear phase response, then it changes the shape of the signal in the time domain. So let me summarize all this. A system that implements a pure delay, in other words, that does not change the signal shape, is the exact same thing as saying that the system has a linear phase response. And in particular, if it delays by k, then that's the same thing as saying the system phase response is going to be minus k times omega. So this is the important walk-away conclusion from what we just discussed.